Dear classmates, welcome back to the FaultModeling. In this video, we are going to introduce the concept of fault detection, and we will go into more details about fault coverage. Then we will conclude this chapter. A pattern detects a fault if the output of the faulty circuit is not the same as the output of the corresponding good circuit. For the following example, suppose we have E stuck at 0,4 here. When we apply the pattern 0011, the good value at signal E is 1, but the faulty value is 0. We use this notation. On the left hand side of the slash is the good value. On the right hand side is the faulty value. We can observe that the good output F is 1, the faulty output F is 0. So we set this test pattern ABCD equal to 0011 detect the E stuck at 0,4. A fault is detected if two conditions are satisfied. Number one condition, the fault activation condition. A fault is activated when we control the logic value at the fault site to a different value as the stuck value. For example, if we want to detect E stuck at 0,4, we need to control E to a good value 1. So we apply input pattern CD equal to 1, 1. Number two condition, we need to propagate the fault effect to any one of the primary output. Again, for this example, we want to control this fault effect to the output. Therefore, we need to apply 0, 0. By the way, signal X is sensitized to an output if the output changes when X changes. For example, signal E is sensitized to the output F. A path of sensitized signal is called sensitized path. For example, EF is a sensitized path. The concept of sensitization will be discussed in more details in our future lecture. In summary, fault detection requires two conditions. Number one, fault activation, and number two, fault effect propagation. We can classify the faults according to whether they are detected or not. In the first class, we have untestable faults. Those are the faults that cannot be detected by any test pattern. Untestable faults are also known as undetectable faults, but this name is very confusing, so we are not going to use it in our lecture. And the second class of faults are called testable faults. Testable faults are faults that cannot be proven untestable. In this class, we can further divide the faults into detected faults, undetected faults, and some other faults such as oscillatory faults or potentially detect faults. The last two categories will be discussed further in the fault simulation lecture. Now let's go into more details about untestable faults. Untestable faults are the faults that cannot be detected by any test patterns, and it has been proven by our ATPG tool. Untestable faults are also known as redundant faults. Proving untestable fault is NP-complete. so it's a very difficult job. The complexity is the same as satisfiability problem. Examples of untestable faults include the following. Number 1. Redundant circuitry. For this example, we have a 3-input OR gate. The third input, A2, is tied to input A. So A2 stuck at 0 fault is untestable. No matter which pattern we apply, we cannot detect A2 stuck at 0 fault. The second example of untestable fault is unused output or tied input. Take this 4-bit parallel adder for example. Typically, we tie the carry in to 0. Because C0 is tied to 0, C0 stuck at 0 fault is untestable. And sometimes we discard the carry output, so C4 is not used. Stuck at 0 fault or stuck at 1 fault are untestable on C4. The third example of untestable fault is a hazard control circuitry. From fundamental logic design, we know that AB prime plus BC plus AC can be simplified to AB prime plus BC. The term AC is actually redundant. From this Carnot map, we can see that the circle of AC actually has no function contribution. The reason why we have this AC gate is to prevent hazard. So AC output stuck at 0 fault is actually untestable. Number 4 example of untestable faults are error control circuitry. Suppose we have 2 copies of identical circuit, A and A+. Their inputs are tied together, and their outputs are always the same. After a tree of exclusive OR gate, which is error control circuitry, ECC, the output is always 0 if there is no fault. So, output stuck at 0 fault at the ECC circuit is untestable. Finally, the 5th example of untestable fault is ATPG constraints. For example, sometimes we set a certain primary input to 1. In that case, the stuck at 1 fault is untestable. So now let's go into more details about undetected faults. Undetected faults are those faults that are not detected by the given test set. Undetected faults are due to ATPG runtime limitation. The number 1 reason is that we cannot prove it untestable. As we mentioned earlier, proving untestable fault is NP complete, so we cannot prove it untestable within a limit runtime. The second reason is that we cannot find the test pattern for this undetected fault either. So we are not sure what happens to those undetected faults. Please note that don't get confused about untestable faults and undetected fault. Untestable faults are those faults that have been proven to have no test pattern at all, while the undetected fault has no test pattern so far, but actually they may exist pattern, but we are not sure. In summary, untestable faults are not the same as undetected faults. So here is a quiz. Suppose we have this circuit and we apply the first two patterns 000 and 001. Consider only the 6 faults on fan out E and their branch L and F. Which faults are undetected? Have you got it? From this table, we can see that E stuck at 0 is detected. F stuck at 0 is also detected. But L stuck at 0 and L stuck at 1 are not detected. So the answer is L stuck at 0 and L stuck at 1. Quiz number 2. Now, let's consider all the 8 test patterns. Can you tell me which faults are untestable? Have you got it? Looking at these 8 test patterns, no pattern detects L stuck at 1 fault. So L stuck at 1 fault is untestable. Now let's revisit the concept of fault coverage. In our previous lecture, we talked about fault coverage. Fault coverage is a good measure of test set quality. The definition is the number of detected faults over the number of total faults. However, now that we have the concept of untestable faults and the testable faults, we can further modify this coverage into test coverage, which measure the quality of test set, but we consider only the testable faults, because untestable faults do not have any impact on our test quality anyway. So in the denominator, now we have only testable faults. As you can see, the number of test coverage must be greater or equal to fault coverage. And the third matrix is ATPG effectiveness, which measures the quality of our ATPG program. In our ATPG, we can either generate a test to detect the fault, or we can prove a fault untestable. Those two are the contribution of our ATPG, so we put them in the numerator. So now let's have another quiz. Suppose we have a circuit which has a total of 1,234 faults, out of which 1,000 is detected. 230 faults are untestable. 4 of them are undetected faults. Now, please tell us what is the fault coverage, what is the test coverage, and what is ATPG effectiveness. Have you got it? Yes. Fault coverage is the number of detected faults over the number of total faults. Test coverage is the number of detected faults over the number of testable faults, which are 1,004. ATPG effectiveness is the number of detected faults plus the number of untestable faults over the number of total faults. So here is the answer. Now let's revisit this equation. In our introduction, we said that defect level is equal to 1 minus yield to the power of 1 minus FC. So in practice, does 100% fault coverage equal to 0 dPm? If we plug in this equation, it seems that defect level would be 0 if fault coverage is 100. But in practice, the answer is no. 100% fault coverage cannot guarantee 0 DPM because fault coverage does not represent defect coverage. Suppose that the big circle here is the total number of faults, and the inner circle here represents the detected fault. With this fault model, we don't know how to translate this into defects. We don't know what's the number of total defects. We don't know what's the number of detected defects. So actually, we don't know what's the defect coverage. The reason is because sometimes one defect can be modeled by more than one fault. For example, suppose we have a bridging fault between input signal B and the ground. This defect can be modeled as a B stuck at 0, single stuck at 4, or F stuck at 0, single stuck at 4. You can also model it as B slow to rise transition 4 or gate delay 4 in gate G. So this is a one-to-many mapping. On the contrary, sometimes one defect cannot be well modeled by any fault. For example, slow process cannot be well modeled by single stuck at fault. Maybe we can model it as path delay fault, but it is out of the scope of single stuck at fault. A second example, reliability defect cannot be well modeled by single stuck at fault. We also talk about fault masking of multiple stuck at fault, which cannot be modeled by single stuck at fault. There are many other cases where defect cannot be modeled by any fault. In conclusion, fault model is a very important concept for test automation. With fault model, we can automatically generate test patterns. We can also quantify the quality of our test patterns. Although we have introduced many fault models in this chapter, but only a few of them are used in practice. First of all, single stuck at fault model is applied for sure. Then, some company will choose to use transition fault model. Other fault models are adopted according to the company and the product's requirement. Please note that fault model can be deceiving. Fault models do not always match the behavior of defect. According to the experimental result from Stanford, only 1/3 of the defect behave like single stuck at fault. Fortunately, many of the defects can be detected by single stuck at fault test pattern. And we also mentioned that 100% fault coverage does not guarantee 0 DPM. Stanford research showed that there are some test chips that escape 100% single stuck at fault test sets. If you think 99.9% fault coverage is very good, then you might need to consider this case. If 99.9% is good, then 2 million documents will be lost by IRS, Internal Revenue Service, this year, and 12 babies will be given to the wrong parents today, and etc. Because there are many faults in a circuit, even a small delta in fault coverage makes a very large difference. That's the end for the fault modeling chapter. Thank you for listening.